Okay, come on. Okay, so let me bring back you guys out there in Zoom. All right, so now we're in business. So this is what I'm going to do every class. I'm going to record the lecture so that, I'm going to post it in the module section so that you guys can have access to it.
You have to watch the recording.
Yeah.
Just in case you miss class or you just want to hear my voice again. I don't know. All right, so let's talk about chemistry. So as I was saying, chemistry is that area of science which deals with the composition, structure, properties, and reactions of matter. And we try to understand, we not only observe, these things, but we try to understand these things at the microscopic level, at the level of atoms and molecules, all right? So at the heart of chemistry is matter, right? Matter, by the way, by definition, is anything that has mass and volume, right? Anything that is material, right? So, as we said before, in chemistry, we are concerned with the composition. What do we mean by composition? It's makeup. So, for example, to use a simple example, water is about 89% oxygen and 11% hydrogen, right? So those percentages represents the composition of water, all right? And we're concerned with that. We need to find out how much of each element is present in a particular substance. Then we're concerned with the structure. Now, what do we mean by structure? Basically, we're talking about how the microscopic particles are connected or put together, right? So again, using water as a simple example, water, as I said before, is made up of hydrogen and oxygen. And it turns out that in the structure of water, and I should have brought my tablet with me to write this down, but I can describe it, I think. So in the case of water, and you're going to learn about this later on anyway, in the case of water, if you look at a molecule of water, you're going to have an oxygen atom, which will be simultaneously linked to two hydrogen atoms, right? And that's basically the structure of water. There's some other things that come into play, such as angles and polarities and so on. But in terms of the structure, what we're concerned about is how the atoms are put together, all right? And then we're concerned with the properties. Now, this term in chemistry and sometimes in physics basically means the defining characteristics, right? So we're talking about things like color, density, boiling point, freezing point, odor, all those things that you can use to define a substance. We call them properties. And later on, we're going to learn that there are two types of properties. You have physical properties and you have chemical properties, all right? And we'll get into that later. I won't go into that right now. And then the final thing that we're concerned with are the type of reactions that substances will undergo, right? And when we're talking about reactions, we're talking about chemical changes, where you start off with one substance, and then at the end of the reaction, you're going to end up with different substances. The substances that are the products will be different from the substance that you started off with, right? So these are all the things that we are interested in when it comes to this particular science, chemistry, all right? Now, of course, I'm biased. So in my opinion, chemistry is the most important scientific discipline there is, right? I'm quite sure my colleagues in physics and biology would probably differ in terms of that opinion. But that's what I say. So, and this basically illustrates this fact, right? Chemistry is very important because it's basically connected to other disciplines and also affect us in our everyday life, right? So that's why I like this diagram right here. It shows you the connection between chemistry and other sciences, such as medicine, toxicology, biochemistry, pharmaceuticals, engineering, forensic science, nutrition. All of these would not be possible in terms of studying and understanding them without understanding basic chemistry, all right? Even physics, right? In fact, for most sciences, if you're going to college and you plan to study, let's say, biology or physics or whatever, chemistry must be a part of your curriculum in terms of the program that you're doing, right? And that's because understanding chemical principles will go a long way in terms of understanding stuff in biology, stuff in physics, and so on, all right? But not only that, chemistry is also important when it comes to certain aspects of law, right? Chemistry is obviously important when it comes to education. Also business, right? Because if you're talking about chemistry, more than likely, you will talk about the chemical industry, right? You know, the type of materials and pharmaceuticals and agricultural products, fertilizers and so on that are made by such industries, and therefore there's a business aspect to it, right? Electronics, and so on and so forth. So that's why one thing that we in chemistry like to say is that chemistry is the central science. All other sciences and other aspects of life actually is related to chemistry in some way or form. All right. Okay. So we're going to take a bit of a brief detour to talk about the scientific method. All right. The scientific method is basically the method that is used by scientists to explain observations in nature. All right. And there are several steps involved in this method. So the first step is where we define the problem by recognizing it and stating it clearly. All right. This step is called the observation, right? So basically you're using your senses, your eyes, sense of touch, what you hear, what you smell, even though I would not recommend that you go about, dipping your nose into a test tube to sniff anything that you don't know about, all right? But, you can use your senses to determine or to observe what is happening, right? So we call this the observation. The next step is where you put forward a tentative explanation for what you observed in the first step. Now, this explanation must not only be tentative, but it must be reasonable, all right? It must make sense, right? We call this the hypothesis, all right? The next step is where you decide on how to test this hypothesis. And this is where the difficult and hard work of the scientist is involved. Because in the natural sciences, the way we test an hypothesis is that we have to come up with an experiment, right? Firstly, we have to basically come up with an experimental design, the purpose of which is to simply test to see whether or not the hypothesis that you put forward can stand up to scrutiny, right? So basically you design the experiment in order to cause the hypothesis to fail if it is not true, all right? So that's basically what the hypothesis is. You have to come up with an experiment and you have to test the hypothesis. Now, when that happens, what you'll find, and this is usually the case in the initial stages, right? What you'll find is that the data that you get from the experiment will not agree with what the hypothesis says, right? So when that happens, what you'd have to do is change the hypothesis, right? Or modify it in some way, right? And then you test it again, right? And this is something that is repeated over and over again, right? The hypothesis is tested, right? The data does not fall in line with what the hypothesis predict. You go back to the hypothesis, you change it, or you change the hypothesis, or you modify the hypothesis in some way and test again. And you do that over and over again until you get some consistency between what your experimental results end up being and what the hypothesis would predict, right? So what is observed after that, we call that the scientific law, right? The scientific law is basically a statement which says that when this happens, this happens. This is what we observe when we conduct the experiment, and this is basically the result. And the scientific law is very useful because it can help you to make some predictions about a particular phenomenon. Now, the refined hypothesis, after repeated testing and experimentation and so on, and when that is done over and over again, you're going to end up with what is called a theory. So the refined hypothesis is basically what we call the theory. And basically the theory is a statement or an explanation, I should say, or a model, which is backed by the evidence or the data arising from repeated experimentation, all right? So that's the theory of any experiment that you're going to do. Just to give you one example, later on in chapter 10, I think it is, we'll be dealing with gases. And one law that we will discuss is Boyle's law, right? Now, Boyle's law basically says that the pressure of a gas is inversely proportional to the volume. Basically what that means, and we're going to learn more about it later on, but basically what that means is that as you reduce the volume of a gas, the pressure increases, right? So that's basically the law, right? It predicts the relationship or explains the relationship between the pressure and the volume. But the theory is different. The theory is used to explain why we observe what we observe in the law. And the theory that we're going to look at, again, that's in chapter 10, is called the kinetic molecular theory. And basically that theory uses the idea of the fact that the gas consists of particles, high energy particles moving around, and they will collide with the walls of the container. And that collision will cause pressure to be exerted on the walls of the container. And when you reduce the volume of the gas particles will hit the walls of the container more frequently, exert greater pressure. So that's basically showing you the relationship between the scientific law and the theory. So as I said before, we're going to discuss that later on in chapter 10, I think. Now, what I'm showing you here is basically a flow chart of the same thing that we just discussed. But there's one thing that I didn't discuss, right? So just to briefly go through the initial parts, observation, of course, what we see, observed it, and so on. And we may observe like a little pattern in terms of, what we're observing. And then we come up with an hypothesis, which, as I said before, is a tentative explanation of what we observed in the first step. We do experimentation to test the hypothesis. As I said before initially, you might find that the data from the experiment does not fall in line with the hypothesis. So you have to come up here. You either have to replace this hypothesis or modify it to fit the data, and then you do more experimentation. So this part here is done over and over again until the data that is obtained by experimentation becomes consistent with the hypothesis. And when that happens, we end up with a theory. So the theory is basically a hypothesis, accepting that it has data that is backing it from repeated experimentation, all right? Now, one thing I did not mention is this last step here, further experimentation, because even though you might have a theory that has been established, repeated experimentation and so on, and, the scientific community accepts it, there may be persons, or there have been persons, who are tinkering in their lab, always testing the theory, right? And what has happened in, if you look at scientific history, is that in some cases, you might have a well-established theory that has been debunked because somebody somewhere did some experiment to test the theory, and the theory does not work based on the most recent experimental data. And when that happens, basically what that means is that we have to discard the original theory and come up with a new theory, or change the theory, modify it so as to fit the data of the most recent experimentation, all right? So that's basically, this flow chart here basically summarizes well the scientific method. Let me see if I have a tablet, because, okay, good. Do I have the... all right, so I want to show you an example of how this works. This is an actual historical example. Let me just connect this up here. Okay, let's see if this is working. Okay, so what I'm going to do is, oops. I'm going to introduce a new slide here. Okay, and then, okay, so there was a guy oh gosh, I forgot his name. But anyway, he's a chemist, or was a chemist. And he was trying to make this compound. Well, he was trying to isolate this compound. Okay. Ammonium cyanate. And he did several steps before getting the compound in an aqueous solution. Okay, so this is, I hate when this happens. Let's see if I can get rid of that. Okay, so this is the compound. Anyway, I give up. So this is the compound that he's trying to isolate. So he did a series of reactions and he ended up with this compound. The name of this compound is ammonium cyanate. All right. Now, normally, when you have an ionic compound in an aqueous solution, in order to isolate the compound, you would heat the solution and that will drive the water off and you'll be left with the solid ionic compound. And that's what he tried to do, right? Now, what he ended up with is forming this compound. And the name of this compound is urea. Now, why is this important? This is important because before this, there was a theory known as the, I can't believe this is escaping my memory now. But anyway, hold on, let me see if I can find it over here. I remember now, it's called the vitalistic theory. Okay, so according to the vitalistic theory, let me write this down here. Okay, so according to the vitalistic theory, all right? Now, according to the theory, basically what this theory says is that naturally occurring compounds, especially those compounds that you'd find in the tissues of plants and animals, cannot be made by man or human beings, right? There's this vitalistic force out there, according to this theory, there's this vitalistic force out there in nature, which is necessary for the synthesis of these compounds, right? Well, it turns out that this is a compound that you'll find in nature, right? The compound that this guy, I remember his name now, his name is Wooler, right? That's me, yep. I'm all right, long time no see. You too. Okay, so as I was saying, Wooler actually made this particular compound, which is a naturally occurring compound. So because of this discovery, because of what he did, that signaled the end of the vitalistic theory as a reliable theory that scientists can look to as an explanation for the existence of these compounds, all right? And this is just one example, and there are several examples of theories that have been knocked down because of discoveries made by scientists. In this particular case, this discovery was totally by accident because Waller was not trying to go there to try to contest or see if this theory would work. He's basically, all he was trying to do was to isolate this compound, and he accidentally made this compound, which basically results in this theory not being valid anymore, right? So we refer to the vitalistic theory simply as a relic, all right, and not anything more. Okay, so that's just one example. So let me just highlight some definitions that we talked about earlier. I need to reiterate these so that you understand what we're talking about. And this is also very important, the difference between a hypothesis and a theory, right? So just to recap, the hypothesis is basically a tentative explanation of what we observe, right? We have not done anything to say whether or not it's true. Basically, we're just coming up with an idea to say, okay, this is a possible reason why we observe a particular reaction or whatever. The theory is basically a well-established hypothesis, right? This is comes after you have done repeated experimentation, which results in repeated refinement of the original hypothesis. So you do experimentation, the hypothesis is either modified or changed as a result of the data collected initially, and then you test that new hypothesis again, and you do that continually until you get some harmony between the data collected and the hypothesis. When you get to that stage, then that hypothesis is now a theory. So as stated here, it's an explanation of the general principles of certain phenomena with considerable evidence or facts to support it. And those two are different from the law or a law, right? The law is basically a statement of what is observed, right? So as I said in the example earlier, remember the example of Boyle's law? There's an inverse relationship between pressure and volume. That's basically a statement, which is the law, right? You're just observing what is seen, and you make a statement about that. And that is different from the theory, right? And very often people tend to confuse the theory and the law. Even, I've seen well-established professional scientists using those two terms as if they mean the same thing, but that is not true, right? The theory is an explanation based on data collected. The law is basically a statement of what is observed, for which there are no exceptions, right? So that's basically the difference between the law, the theory, and the hypothesis, all right? And the next slide basically gives you a bit of a flowchart which compares the hypothesis to the theory. And again, we're highlighting the differences between the two. So in the case of the hypothesis, it's a tentative explanation of what is observed, but the theory is basically the explanation which is backed by the data that is collected as a result of experimentation, repeatedly testing your hypothesis. So as stated here, the hypothesis provides a basis for further experimentation so that you can get to the theory, while the theory already has the evidence and data and facts to support it. Okay, so with that said, let's move on to an actual everyday example, because believe it or not, even though this might be the first time you're meeting this whole idea of the scientific method, right? But you may not recognize that you have actually been using the scientific method to solve, trivial problems that you may be encountering in your everyday life. So let's use this particular example. Let's say you want to play your CD, your favorite CD in a CD player, right? And the CD skips, right? So in the scientific method, this would be your observation, the very first step in the process of solving this problem, right? So the next step would be your hypothesis, right? Now, when it comes to this, there are two possible hypotheses, or hypotheses. I think that's a plural of hypothesis. One would be that something is wrong with the CD player. The other would be that something is wrong with the CD itself, right? So let's deal with the first case. What if the CD player is at fault? How would you test to see if that is so? Exactly. So you replace the CD that you want to play with another CD, and in this particular case, the sound is okay. So the conclusion we can come to is that there's nothing wrong as far as this is concerned, nothing wrong with the CD player. Okay, so that leads us now to the second hypothesis, which is that something is wrong with the CD itself. So how would you test this particular hypothesis? Anybody? Exactly. And in this particular case, when you do that, then the sound still skips. So what does that indicate? That there's something wrong with the CD. So this is a simple example, admittedly. But this is just illustrating, the type of logic stepwise that is involved in a scientific method. Okay, now one more thing. What time is it, by the way? Okay, I should be able to do this in the next 7 minutes. One thing I want to highlight about the scientific method, which will be very important, especially for those of you who are considering pursuing a career in science, technology, engineering, and math. And I want to go back to this particular slide right here. Okay, so we went through this before, right? And we talked about this part right here where you conduct after you have, put forward a hypothesis, you conduct your experiment to test it, and you go back up here. When the data doesn't fit, you go back up here, come up with a new hypothesis, or you modify the original one, do your experimentation, and so on, right? One important aspect of this that I want to point out to you is that when you're getting to this stage right here, you must always, always, always refine or change your hypothesis to fit the data, right? What you should not do is change the data to fit your hypothesis, right? That is basically scientific malpractice, and the consequences of that can be, in some cases, you can probably escape, but in other cases, there are some serious repercussions, all right? And I just want to highlight at least one, if not two, examples of this. Okay, whoops. Now, let me copy and paste this because I want you to see this article. Come on. So, okay, so this lady, she was a Nobel Prize winning scientist, and, did a lot of research and so on. When you get to the Nobel Prize, of course, for chemistry, that's like the ultimate in terms of recognizing your contributions to the science. Well, one day, somebody was trying to reproduce her results for a paper that she published, and they found that the results were not reproducible. All right. And basically, because of that, that paper that she published based on her research was withdrawn. All right. And this is one important aspect of science that you need to understand. When you're doing experiments, your results should be reproducible, which means that somebody else doing the same thing that you did to get the results that you got should get the same results, right? Overall, I mean, there might be some differences in terms of data points and so on, but the results should still be the same. So as a result of this, she had to basically retract her paper. And to be perfectly honest, this is the first time that I know of where scientists actually had to do that, right? So that's just one example. And I don't have time to go into the other example, but I would strongly advise you to read the article for this link right here, where somebody actually committed fraud and ended up in prison as a result of basically playing fast and loose with the results that he had, all right? So you can read that on your own. And that's it for today, all right? So before you leave, guys, make sure that you put your the last sheet of your syllabus, that form completed, just detach it and put it up front. And make sure you watch the videos that I've posted online so that you come prepared for the next class. Yes, ma'am. Oh, that's right here. No, it's only once a week. Yeah, 2 days. Yes, ma'am. Yes, ma'am. You sound like you were lost.
No, I need to, not my class either.
Oh, this is not your class?
This is not my class. I'm really going through it.
Okay, what class are you supposed to be?
On my, yeah, it's not loading, but on it, if I can't get it to load, it says I have you for 12.
Oh, that's general chemistry.
Yeah,
Oh, yeah,
okay.
in this class,
At
right
12.
after, right, at
12 or 12?
at 12:30, I'm sorry.
Okay, because yeah, it says 12, and it says.
It should, hold on, let me check and make sure, but I'm quite sure it would have to be 12:30 because this class is at
It might
12.
have just messed up.
It's
12:30.
Yeah, it's 12:30, yeah. Yes, sir.
So when I get home, I'll be able to see what the assignment is.
Well, no, I'll bring the assignment to class. Oh, I'm gonna post the assignment for what we just covered.
Yeah.
But for the next assignment, I'll bring that to class.
Yeah, that's. And I'll also see the file for the notes.
I'm sorry?
I'll look at the files for the notes I can.
Okay, hold on 1 minute. So you're talking about the PowerPoints?
Yeah.
Let's see, oh, lecture note, okay. Oh, okay, so let me publish this here. And let me publish this here, chapter 2. And chapter 3. And now you can see that.
And also, files I can see the assignments.
No, you're right. So as far as the assignments are concerned, I'm going to publish
Just the first one?
just the first one because I'm going to bring the other one to class next week.
Okay.
Mhm. Yes, sir.
Hi, I was a couple minutes late to the class and you're already halfway through the attendance.
What's your last name?
Delgado.
Huh?
Delgado. which
Okay,
is-
I remember calling that name. Yeah, I got you.
Thank you very much.
No problem.
If we have the syllabus, oh, Canvas
Really?
inbox,
I
never
thought
mind,
they
I
were-
see it.
Introductory chemistry.
Okay.
It's kind of like high school chemistry.
No, I took it over this summer.
Oh, okay. Yeah,
First summer A.
at least you get a review or refresh of.
Yeah, I know, I was like really lost, guys, like, I was just like, I'm so sorry, I don't mean to like stress you, but like walking into your class at the end of it and then like.
Yeah. No problem. Ah,
Not to be rude, but you have an accent, where are you from?
I am from, yes.
Okay, guys, I'm gonna be really biased, are you from Trinidad?
No,
Oh,
been there, but no, I'm not from Trinidad.
are you from the Caribbean?
I'm from the Caribbean.
Okay, I can tell. You're not from Jamaica.
Yes, I am.
There's no way. Part.
I am from Kingston. Why? You're from Jamaica?
No, I'm from Trinidad.
Oh, okay.
Yeah, sorry, I thought I heard accents, I had to like speak up on it.
Yeah.
I'm from here.
Yeah, I'm from Jamaica. I've been to Trinidad when was it? 1989,
Oh, that's, wow.
and I enjoyed it. It was
Of course,
nice.
you know, we do run the Caribbean, you know, one of the best.
I was a student at the time. I was a student at UA, but I played basketball for the Mona campus, and we had a tournament in Trinidad.
Mm-hmm.
So
Were you born in Jamaica?
yeah,
I was born here, but my mom, like everyone else in my family was like all born in Trinidad, and my mom here.
oh, okay. Your mom is from here?
No, my mom's from Trinidad.
Oh, okay.
We're like literally from Port of Spain.
Oh,
We're
okay.
gonna like Port of Spain and like also the countryside and like Tobago and whatnot. It's like we're kind of like mush.
Yeah, Trinidad was nice. I have a question for you. Now that you've, is there anywhere around here where I can get doubles?
Oh, like here, like okay, are you?
around like, I mean, Ocala,
Yeah. Oh my gosh. Wait.
because I,
There is.
the first time I had doubles was when I was in Trinidad,
Mm-hmm. Oh yeah.
and
You
I've
know,
never,
make it the best. Make it the best.
I've never had it since.
Oh my gosh. Wait. You should have told me. I just made some last week. Okay. Wait. There's this. Oh my gosh. It probably won't look this class grade, but in Ocala, if you go down by do you know what's the name of the community? Gosh, I don't know, but it's
Iron Oaks?
yeah, by Marion Oaks, kind of. Like by Cedar Road, there's gonna be like a gas station. If you just keep going right, I'll find the address and I'll give it to you. But like, there's a nice like little Jamaican place. Their food is a little bit It's a little bit.
Because
It's not like Jamaican, but it's like Jamaican, like it's like Indo-Caribbean, so it's
Okay,
like
okay,
Indian and Caribbean, so they
okay.
have like the mix. But they make their stuff how like Caribbeans do for
Right,
the
right,
most
right.
part, but it's really good. Don't eat the roti though. Roti's a little bit
Oh, really?
questionable. The roti's very questionable. I don't trust it at all. No, 'cause it made me sick one time.
Or-
I have to, we go up to like Orlando because like that's where like all the stuff.
Yeah,
is.
yeah, I know, yeah, yeah,
It's
yeah.
so far, so it's
Yeah,
like we
right.
literally go up like once every couple months, and we get like a bunch of roast, we get a bunch of doubles, and we just like stack it and we go.
Yeah, the doubles was good, man. When I was in Trinidad, because I had a friend of mine who was a student there, and he took me to a place called QREP. Oh shoot, I missed some questions that were asked online. Anyway, yeah, he took me to a place called QREP. I remember, and it basically was street food. It wasn't in a restaurant or anything like that. And the food was the doubles. I like, what did they put in it? I think they put chickpeas in it.
You make doubles without chickpeas?
Hmm?
You don't make your doubles with chickpeas?
We don't have those. I've never. It's the first time I've eaten
You don't
doubles.
make doubles and chickpeas?
No, we don't have doubles in. That's how that.